Large language models possess immense reasoning capabilities, but their native state is entirely isolated. They operate inside a strict boundary known as a context window. The context window is the working memory limit where a language model processes input text. Everything outside that window is completely inaccessible. Because of this isolation, models are bound by their training data. When a model reaches its knowledge cutoff date, its internal factual repository stops. It cannot query a live database, check current inventory, or read a secure internal document. To build Agentic AI, systems capable of taking independent action to solve complex problems, a model requires continuous, real-time read and write access to external systems. Without an architectural bridge to pull in live data, an AI remains a walled-off text generator, incapable of autonomous agency. To bypass this isolation, developers typically write bespoke API integrations. They build a custom, hard-coded bridge connecting one specific AI model to one data source. Scaling to 3 AI models accessing 3 distinct databases requires maintaining 9 separate connections. This architecture is brittle. If one data provider updates their API endpoint, every hard-coded integration pointing to that database breaks simultaneously. Teams end up dedicating massive amounts of engineering hours strictly to integration maintenance. This creates a severe bottleneck, stalling the deployment of scalable AI agents in complex enterprise environments. Scaling AI agency requires moving away from bespoke wrappers and adopting a universal, open-source connection standard. That standard is the Model Context Protocol, or MCP. MCP replaces the tangle of infinite custom endpoints with a unified, plug-and-play architecture. MCP relies on a strict client-server model. It moves away from direct peer-to-peer API calling, enforcing a hard boundary between the AI application and the data environment. Here are the 4 core nodes of the MCP ecosystem: AI host, MCP client, MCP server, and local data. The AI host analyzes intent and sends a request to the MCP client. The secure MCP server then receives this request and independently extracts information from local data. This separation of responsibilities protects enterprise data by keeping execution logic on the server, entirely isolated from the AI application layer. This raises a critical question. How did the client and server communicate across this strict boundary? They communicate using JSON RPC. JSON RPC is a lightweight data interchange format that allows programs to send structured remote procedure calls back and forth. This diagram shows the primary transport mechanism for secure local environments, Standard Input-Output, or STDI, the default secure data stream an operating system uses natively. For remote connections, MCP uses Server-Sent Events, or SSE, allowing servers to push continuous updates over a single HTTP connection. Standardizing this transport layer carries massive security implications. The large language model operates entirely blind to the actual infrastructure. It possesses 0 database credentials, no direct system passwords, and no root privileges. The transport layer functions as a zero-trust moat. The AI model only ever sees the highly specific, sanitized text data that the server explicitly formats and sends across the boundary. Across this secure boundary, the MCP server exposes 3 foundational capabilities to the client. These are called primitives. The first primitive is known as resources. This diagram displays resources providing controlled read access by extracting specific file data and injecting only targeted information into the model's context window. The second primitive is prompts. The prompts block injects a pre-formatted blueprint into the data stream, filling empty variables with contextual data. By utilizing both resources and prompts, an AI agent can passively consume and format external context on demand. The architecture mathematically standardizes the data flow, completely removing the need for humans to manually copy and paste context into a chat window. Passive reading and templating build context, but agentic AI requires active execution. That capability arrives with the third primitive, tools. This diagram illustrates tools providing write and execute capabilities, allowing tangible actions like altering database records. The critical safety mechanism is authorization. The AI merely requests execution. The server, safely behind the boundary, evaluates the request and retains total authority over performing the action. With the tools primitive, an AI transitions from a system that merely generates text to one that performs secure actions within the software environment. When we zoom out from the individual client-server loop, we see the macro-level impact on enterprise network topology. The earlier spaghetti integration model forced a one-to-one relationship for every tool. MCP creates a clean one-to-N architecture. This diagram demonstrates the efficiency of one-to-N scaling. An engineering team can take a single AI host and plug it seamlessly into a Postgres database, a GitHub repository, and a Slack workspace simultaneously, all through one standardized client. This topology creates strict model portability. If an enterprise decides to migrate away from a proprietary cloud model and switch to a locally hosted open source model, they swap the AI host. They do not have to rewrite a single line of data connection code. MCP decouples the reasoning engine from the data infrastructure. This ensures that as individual AI models rapidly evolve and deprecate, the enterprise tech stack remains stable and future-proofed. We have moved from an isolated text generator bound tightly by its context window to a fully integrated node operating securely within a larger network. MCP establishes a standardized communication layer, allowing developers to treat the model as a modular component within a larger system. It resolves the core tension of AI development, granting models the infinite contextual access they need to be useful, while maintaining the strict zero-trust execution boundaries required to be safe. As the developer ecosystem shifts, universal protocols will predictably replace bespoke framework wrappers. The efficiency gains are simply too high to ignore. Advanced reasoning enables planning, but the model context protocol provides the standardized infrastructure needed for an AI to execute those plans in the real world.